Now, since we are very clear about the concept of, we call it as dispersion, which simply goes like in definition form, we can say that splitting of splitting of white light into its constituent constituent colors. That's basically we call it as dispersion. So suppose if we say that
Sir,
if
your voice is not clear.
okay, if this is a medium, that's, let us call this medium as glass and this medium as air. And then if we somehow we find out that a white colored light is being introduced onto this glass, making certain angle to it, like we can just imagine that there is a white light which is falling at an angle like this. Then our standard rule, wherever we experience that the light is changing its medium, we always have to introduce a normal as our reference and then the laws which we have studied. So from this side, if we say that if we continue its travel in this direction, we call this ray, this extended imaginary ray, we call that as intended path. It is intended path. Now, what do you mean by intended path? Suppose if I remove the glass slab, the light will travel like this. But since we have introduced the glass slab, now something happens which is like this. What is this? We can say that this is a deviation delta for the color red. Similarly, we have got our extreme color as violet, which will show deviation somehow as an example like this, where from its intended path, see the deviation shown by violet color. This is treated as DV. Then the more important term to discuss about here is something called dispersive power. It's a dispersive power. This dispersive power can be calculated as difference between delta V minus delta R divided by the average deviation. And what's an average deviation? We can say that average deviation equals to delta V plus delta R divided by 2. This gives us the dispersive power. Sometimes the numerical problems may be based upon these two. So here was one of the point to be discussed. Then we extend it to the next level, such as now these separated rays basically now they are moving at a different angle, and now they come at this border where they are again experiencing change of medium from glass to the air. So the point where light experiences change in medium, we will always take a reference of normal. And then applying the laws of reflection and refraction, we can simply say that now this light which is red in color will get traveled like this. Just 1 minute. It will travel like this. And the blue colored one and the blue colored one will travel like this. One thing which is important to be noted here, that whatever are the refracted rays after air to glass and again back glass to air, these all rays, they are parallel. That means if I take out the glass, the whole ray pass as a single line and it will come out like this in an intended path. But since we have put up a glass, dispersion has happened. Red colored light has taken its own way, violet has taken its own way. They hit the other end of the glass at different points. They again experience a refraction and they come out. But when they come out, we find out that this ray number, I'll call it as ray number 1, then red ray and the violet ray. They're all parallel. They're absolutely parallel. So we can simply say that this is the glass slab which has introduced this distance between their original track and the new track. This is the distance that has been introduced between their original intended track and the new track. This distance, this displacement rather, we start calling this type of displacement as lateral displacement. This is another concept we must know. It's a lateral displacement. What do you mean by lateral? Parallel. So the ray is parallelly displaced. To make it further simple understanding, let us say that this ray is only of red color light. So I'll draw it here. Let us say that there is a glass slab, and onto the glass slab, we say that we are incidenting a red colored light like this. Then we immediately plot its intended path. So its intended path, somehow it goes like this. Now, because of this air to glass transmission, this red color light will be bent towards normal and it will hit the surface here. Again, there is a refraction and now the red colored light travels like this. If we just ignore these irregularities here, this ray is parallel to this ray. This parallel displacement, which is introduced because of this glass, such displacement is called lateral displacement. So lateral displacement, we can simply define it in definition terms like lateral displacement, it is the distance between the intended path, it's the distance between the intended path and the actual path traced by light. Actual path traced by light. That's what is the simple definition that we can talk about the lateral displacement. Let us consider a situation where a rarer medium and the denser medium is separated by a surface as shown here. So let us assume that this medium is rarer and this medium is denser. So to have this total internal reflection, our first condition is that light must travel from denser to rarer. The very essential condition is that light must travel from denser to rarer one. So let us consider a ray of light which is actually traveling from a denser medium to a rarer medium. So let us consider this is that light, ray of light. Now, since it is changing medium, with our rules, principles, we know that what is the first thing that we need to do is to give normal for the reference purpose. Let us say that this one is the normal for our reference purpose. Now the journey is from denser to rarer. So naturally, instead of going in its intended path like this, just as an example, let me draw it correctly. Like this, instead of traveling in its straight line path somehow like this, it will bend away from the normal. So I can call that if this is ray number 1, it has been refracted, it is refracted like this. So this is ray number 1. So we select now ray number 2. Let us say that we incident ray number 2 with an increased angle. Result of that, the refracted ray will become like this. So if I call this ray as ray number 2, this travels ray number 2 like this, and it appears as ray number 2 here. So now we introduce third ray. Let us say that this third ray is making an angle like this. Let's say ray number 3, which will be now reflected like this. So again, labeling for our convenience, if this is ray number 3, it will travel like this, it will reach to the point, and then it is getting refracted away from the normal. So this is ray number 3. Now, just for a practice part, then we say that yes, we are introducing another ray, which is ray number 4. Please pay attention here, which is with an increased angle. Let us say that this is that one particular ray which we have incident onto the surface, and we know since we have increased the angle of incidence, this ray actually start traveling along the surface of this particular boundary. See the change, see the things, how they are getting changed. First ray, the ray number 1, it was traveling like this. Ray number 1, it traveled like this, it has reached to the point of incident and it bent away. Ray number 2, it is also traveled here and bent away from normal. Ray number 3, again here and bent away. This is ray number 4, which we have drawn lastly. Now this ray number 4 has a one particular angle at which the refracted ray goes along the border of the surface. Now the situation is like that. Suppose if we incident another ray whose angle is greater than this particular angle, like ray number 5, which goes like this. So what is special thing that happens to this ray number 5 is that the refracted ray is completely reflected inside the same material. This phenomena where we can actually experience reflection even if the materials are refracting. Such phenomena is called total internal reflection. Are we receiving reflection here? So yes, it is reflection. Is the surface reflecting? No, the surface is refracting surface. Even if the surface was refracting, still we could manage to have reflection. And when it was possible that we maintain some minimum angle of incidence. This minimum angle, just 1 minute, let me use the saving part. This minimum angle that we have to maintain to get this particular along the border ray, that angle is treated as critical angle. It's a critical angle. So if the angle of incidence is less than critical angle, can we get reflection? No, they are refracted. They are refracted. But if the angle of incidence is that particular critical angle, then there is no refraction. But yes, the refracted ray is traveling along the border of this separation, border of these two particular materials. Now, if we say that the angle of incidence is greater than, if the angle of incidence is greater than the critical angle, this angle we are talking about, this angle is the angle of total internal reflection. So what is the second condition for having a total internal reflection is, we can simply say that angle of incidence must be greater than the critical angle. Then what is critical angle? Again, we can say that critical angle is basically an angle of incidence, an angle of incidence for which the angle of refraction, angle of refraction is equal to 90 degrees. Check critical angle, the one which is in bold line. This is critical angle. For that critical angle, check what is the angle of refraction. It is 90 degrees. So while defining critical angle, we need not have to say that it is angle of incidence for which the refracted light travels along the border of the media. That's not the proper way of definition. That's not the proper way of defining. We define it in such a way that critical angle is the angle of incidence for which the angle of refraction is equal to 90 degrees. And then only it is possible to have total internal reflection using a refracting surface. So revising, what happens to the, what exactly is the total internal reflection? It is the phenomena in which the refracting surface shows reflection. Does it happen for almost every condition? Absolutely not. There must be two conditions that to be satisfied. Very first thing, light must travel from denser to rarer medium. Means for our calculations in numerical parts, we basically must take into consideration refractive index when the light is traveling from denser to rarer. This is more important. May make mark on this. The examiner generally tricks onto these values. So we have to take refractive index of denser to rarer transmission. First condition. Then the second condition comes like the angle of incidence must be greater than the angle of critical part. If these two conditions are satisfied, then and only then we will get total internal reflection. And that's what exactly is the another condition for happening of rainbow. Yesterday we discussed rainbow to an introductory level. Let us continue that example today. Let us say that this is that water drop. We are standing at this position and the sun is like this. So we are in between the sun and the water drop. Now the ray of light travels from the sun. Somewhere it hits the water drop, making an angle. Now, the moment it makes an angle with this water drop, first phenomena that happens is a dispersion. So red colored light goes like this, and the violet color, it goes like this. Now there is a condition that must satisfy. The angle with which these two rays, they are hitting the other side of this water drop, there they must satisfy the condition of total internal reflection. Suppose if they do not satisfy the condition for total internal reflection here, the red colored light will go like this, and the violet colored light, if I just draw the part, violet colored light will go like this. Will this person observe the rainbow? Absolutely not. They are not observable here. They should reach to the eye. So in this case, what is more important is that when the light is traveling from air into water, rarer to denser, there is no chance of total internal reflection. Reason, the first condition itself is denser to rarer, whereas here the light is traveling from air into water. So here only dispersion takes place. Now the light travels on the other edge, and now it is trying to travel from, let's say, from water to air. So first condition satisfied. If second condition also satisfied, then and only then we experience that this ray, it reflects completely. So sorry. This is total internal reflection. Similarly, violet, even that violet reflects internally and it reaches here. So what is happening onto this side of this water droplet is the total internal reflection. Now they come onto this side. At this border again, the transmission is from water to air, denser to rarer. So there is a chance of total internal reflection. But at this point, total internal reflection should not happen. If the total internal reflection happened, red colored light will again bounce back into the same water droplet. So to observe a rainbow, here the total internal reflection should not happen and the ray should reach to the user. Once the rays are delivered to the user side, rainbow can be easily observed. Fine. So to have an observation of rainbow, at this point, what happens is the dispersion, only dispersion. What happens at this point is a total internal reflection, this side. What happens at this side is a normal refraction. It's a normal refraction. If this thing happens, we get rainbow. And that's where basically total internal reflection plays its role. If the conditions are not satisfied here, as what we mentioned onto this part, these lights, they will keep on traveling in their forward direction. User will not be in a position to observe the rainbow. Is it okay?